Hi everyone, welcome to this session. So today we are going to discuss on second order circuit, mainly RC circuit. Okay, and today we have Anindo. So Anindo will discuss with us. Okay, so let's start today's discussion. Okay, so now first thing is what is a second order circuit? Okay, so second order circuit means there are two poles, right? Two pole system. Okay, this is also called second order circuit. Okay, second order circuit. Okay, so now for a two pole system, the transfer function V out, like the voltage input voltage output, transfer function will be like that. Okay, it will be k times omega n square divided by s square plus 2 zeta omega n into s plus omega n square. Okay, so this is, so here k is a constant. Okay, so this is the general formula. Okay, so general polynomial we can say. Okay, so k is the constant here, and zeta is called the damping factor. Okay, damping factor. Omega n is called the oscillation frequency, let's say oscillation frequency. Okay, so this is the thing. Now what is the physical significance of damping factor? Anindo will tell us.
So physical significance of damping factor is nothing but, so when you have a second order system, uh, okay,
Okay,
let me.
let's say we have a system like that. Okay, this is a second order, and here is input and here is output.
So the damping ratio or the damping factor actually is a dimensional quantity. So it actually measure how oscillation in a system decay, how oscillation in a system decay after a certain disturbance.
Okay, so let's say this circuit is in feedback or not. Okay, so let's say we are putting a disturbance here. Okay, some small disturbance. Then the damping factor says that how quickly the output or the waveform will decay, and it gets its stable form.
Steady
Okay,
state or stable
steady state
form.
or
Yes. Yes.
stable form. Okay, so this is the
Okay.
like the physical significance of a damping factor. Okay, so now
Yes.
here are some step response of a of some circuits with some different zeta values. Okay, so we know that the Laplace of a step is nothing but 1 over s, right? So here is written that. Okay, now this table is very important. Okay, for us. So we are not going to deep into the physics of this. We will just like take it granted. Okay, so for a undamped system, the zeta value is 0. Okay, for a undamped system, and the like the V out response, like the output response will be like that. Okay, with respect to time. And in this case, if the poles are conjugate like that, if the poles are conjugate, then we will find this type of behavior. Okay, that is called undamped system. Now then comes when the zeta is less than 1, that is called underdamped system. Okay, then the two poles of the system is complex conjugate poles. Okay, so now if this is complex conjugate poles, in time domain the response will be like that. Okay, so it will go up, like there will be overshoot and undershoot, and eventually with respect to time it will settle. Okay, right on, it will keep decreasing.
Yes. Yes.
Now
Yes. Yes. Yes.
when we have zeta equal to 1, then it is called critical damping. Okay, then and when the critical damping is happening, when the two poles are reals and both are equal. Okay, when the two poles are reals and are equal, okay, there are two poles, then it is said to be a critical damped system. Okay, and the the behavior of the settling is like that. Okay, so it will goes like that and it will settle. Okay, now when we have a zeta value greater equals 1, that is called the overdamped. Okay, now if the poles, the two poles are real and they are unequal, okay, they are, so p1 not equals p2, then the system is called overdamped. Okay, and the behavior is like that. Okay, this is the settling behavior of a overdamped system. So this is for all our step response cases. Okay, step response. Now we will see how it behaves with respect to impulse response. Okay, if we have a second order system like that and we have a voltage impulse and we have a voltage output like that, so this is a second order system. Now, so these are the quantities you can see, so I am not going to discuss, I will discuss only overdamped case. Okay, so actually, so if you let's say if you feed a step to the system, second order system, but you will find the transfer function having a zero at zero frequency. Okay, let's say k times something. Okay, so this case, in this case, even though it is a impulse input to the system, it will, like, no, so even it is a step input to the system, it will behave like a
Mhm. Mhm.
impulse input of the system. Okay, if there is a zero frequency at zero. Okay, right, Anindo? So then the
Yes, yes,
system
yes.
will behave like a overdamped case. Okay, like that, for a step input. Okay, so i
Yes.
am i am feeding a step input to the system, but the transfer function of the second order circuit having a zero at zero frequency, then it will behave like a impulse input to the system, right? And then the curve will be looking like this, so instantly it will charge and then it will decay. Okay, and this is called overdamped
Yes.
system, and here the zeta is equal to n, and the both of the conditions are same for the pole locations. Okay, like if there is two unequal real poles, then it will behave like a overdamped system and zeta equal to 1. Okay, so now
Yes.
we will see some examples and we will understand. Okay, now first thing is how to check the order of the circuit. Okay, so now let's see some example of some second order circuit. And okay, so let me copy the circuit. Okay, so now first of all, we have to find which order circuit is this. Okay, right? So now
Yes.
we can see that there are two capacitance and two resistance present there, so we can independently set these two voltages, right? The like what I can say, uh, like we can independently set the voltage across these two capacitors, so the circuit must be second order. Okay, and again, like in different way we can also think that both the current through each capacitance is not same, right? So that means
Yes.
the order of the circuit must be second. Okay, so this is how we can comment on the order of the circuit. So this is the second order circuit. Okay, this is like this is done. Okay, we have found the circuit is second order, so this is a second order circuit. Now, so this is a step, right? Let's say this is 5 volt step input. Okay, now, so at t equals 0, the cap is behaving like a short circuit, right? So now what will be the V out? So if this is short and if this is short, so the output is nothing but 0, right? 0 volt.
Mm.
Okay, so and t equals infinity, the capacitor are open, so this will be open circuit and this will be open circuit. So you will think the output is the circuit will be looking like that. So output will be nothing but V in itself. So this is 5 volt. So you will think, so you will plot like that. So this is time and this is, so it was 0 initially and it was 5, right? So you will think the right. So we need to find how it will behaves in this time duration. Okay, so you will be like, if you do exponentially, so it is absolutely wrong, right, Anindo?
Yes,
It
yes.
cannot be
Because this
exponential
is,
because this is not a first
yes.
order circuit. So
Yes, this is
up
not
to
a
that,
first order.
it is okay. Okay, now we need to find how it will behave in this time duration. So we have seen that if the poles are, so we can see that the pole here cannot be imaginary, right?
Yes, because this is a passive circuit
Yes,
and only consists R and C. So
yes,
R and C cannot contribute imaginary pole.
yes. Only R and C cannot give a imaginary pole. If there is a L, then it can be possible, right?
Yes, yes,
Yes. So in this case, no imaginary pole is present. So we have only two cases. It can be like over damped, like it can be critically damped, or it can be over damped, right? So it is zeta
yes,
equals 1 and zeta equals greater 1. Okay. Now we can think that, so in this circuit we can find the two poles approximately. Okay. So the two poles will be nothing but, so we can do the Elmore delay model, right? Or in the
yes, yes,
Elmore delay model. Okay. So there are two time constant or two pole we can say. So first time constant is nothing but R and C. So first branch. Okay. So this is the first branch. Then the time constant T2 is nothing but, so we will remove that capacitor, first capacitor, and making like that. So this is the second case. Okay, so this is the V out thing. So here we can see that this 2R will be added. Okay, R plus R, and
Mhm.
this will be C. Okay, this will be this C, second
Yes,
C. Okay, so here we have two time constant. So we have approximately two poles. So P on will be nothing but, and both are left of plane. We all know, right? So this will be 1 over T on. So this will be 1 by RC, and it will be P2 minus 1 by 2RC, right? As here
yes,
R, like both of the resistances R and R, right? So there are two poles. So we can see that both poles are unequal. Okay, so both poles are real and unequal. Unequal. So now which type of damping is this? So this will be
it is
over
overdamped.
over damped. Yes, over damped circuit. So how the like the waveform will be looking like, the behavior? So it will be critically damped, right? So it will be like that. So waveform is not so good. Okay,
Yes,
I am drawing again. Okay, so this is not exponential. That is the main takeaway. Okay, not exponential.
you can plot also the waveform of capacitor across the voltage second capacitor. So we can see you can see there is a certain delay between these two waveform.
Yes, yes. So okay. So you can think as well that. So, okay, let me draw the picture again. So you can think in that way as well. Okay. So this is a integrator circuit, and that is another integrator circuit, right?
Yes, yes,
So
yes,
so let's say this is C1 and that is C2, and C1 equals C2. Okay. And so if this is a integrator and we are feeding a input of step, so what is the output at this node? It will be like a, so it the, we know the sorry. So if the input is step, the first output will be nothing but exponential. We all know,
yes, yes,
right? So basically, you can think that the output will be nothing but like the like the what I can say. So this will be, so this output is exponential, right? And we are integrating a
yes.
ex, right?
Hmm.
So it will be a exponentially things, like almost exponentially thing, but with a delay, right? Because from
Yes,
here
yes, yes,
to there is a delay, right?
yes, yes,
So actually the conclusion is this is not the exact exponential thing, but you can think this is a exponential with some delay. So it becomes not an exponential. Okay, this is the takeaway. So this is the thing, as like you can think it in this way as well. Okay, so what we have said that, okay, let me see. So we said that if the two poles are real and unequal, then it will be overdamped and the system will be behaving like that. Okay, so this will be like that. Okay, so this will be the final VC2.
ye-
Okay, now okay, so this is okay from my side. So Anindo will be solving question 2 and 3. Okay, so let's see. Okay, so actually to solving second order circuit is not so easy. Okay, so actually we are doing some like we are taking some data from our take for granted, and we will be talking about intuitive analysis in another session. Okay, Anindo, like we will be not doing some this type
Yes,
of
yes.
calculations. Okay, we will be fully doing on
Mhm.
time domain. Okay,
Okay, okay.
so main takeaway is this is not exponential in this time duration, but the VC1 can be exponential if we are neglecting this loading effect. Okay, if we have to neglect this loading effect. Okay, loading effect is, let's say, neglected. Okay, like we are
Mhm.
assuming there R2 C2 is very large, right? Very large.
Yes,
To
yes, yes.
comment that this voltage will be an exponential, almost exponential. Okay, so I am
Almost
yes,
exponential.
almost exponential. So I am stop sharing on will share. Okay.
Okay, okay. Just give me
Mhm.
few seconds.
Take your time. Yes.
Is it visible?
Yes, visible.
Okay. The my screen is visible. You can see the circuit drawn here.
Yes.
Okay, so just let me copy those things. Okay, now about the second circuit. So you can see this circuit is almost similar about the previous one, but here is a some buffer is present. So I first so and we take the gain of this buffer equal to 1, and it is a completely ideal buffer. So the our input okay. So and for the and from the previous section we can also say that we can independently set the voltage across to capacitor. So this is again a second order circuit, but here we can directly here we can directly uh, comment about the pole location, because a buffer is inserted in between these two nodes. I
Yes, basically the
rename.
buffer is isolating the both of the branch.
Yes, I just point out the two node A and B. So this is the ideal buffer, and the input impedance is high. So the two node are completely isolating with each other. So this one R and C give our a pole P1. Let's say 1 over R1 C1, and this R2 C2 section will give us another pole location 1 over R2 C2.
So in
Here
this
is a
case
minus.
there is no loading effect thing. Okay.
Yes, there is no loading effect thing. And now our question is how the out. So suppose we apply a step input here, V in. Suppose this is a 5 volt step input. Now the question is what will be our V out? How V out will be behave? So in previous section we say that so this is basically isolate as the A and B node are completely isolated. So the if I applied a step here, the voltage across this capacitor C1, that means at VA the output will for will this R1 C1 for section is acting as an integrator, and the V out will all sorry the V out will exponentially rising. And what about the VB? That means here also the output is almost exponential, but with a certain amount of delay of the buffer. And if I comment about the pole, if C1, if R1 C1 and R2 C2 are equal, that means if R1 C1 and R2 C2 value are equal, so the two poles are locating exact same point. So then the system will behave as the system will behave as critically damped, and if R2, R1C1 and R2C2 are different, then the system will behave as overdamped system, right?
Yes, yes. So for these both cases
And
also please draw the waveform, right? We should write.
yes, yes, yes.
We should draw.
Hmm.
Okay,
I
Anindo,
first,
Anindo. For the second case, write the conditions where R1 C1 not equal R2 C2. Okay.
yes, yes.
A second.
Okay. R1C1 not equal to
Hmm.
R2C2.
Exactly.
Hmm. So when the system is, so when I take R1C1 equal to R2C2. Okay.
Hmm.
So this is, that means it is a critically damped system. That means our zeta is equal to 1, right? Correct me if I am, if
Yes, yes.
I saying something wrong. So the V0 will just exactly, and suppose this is our, sorry, this is
Time
time.
axis. Yes.
And suppose this is our V in, a step response, about 5 volt. Our V out just follow exponentially the output. Maybe it not look like exponentially, but
Not
okay.
exponentially, but it will be critically damped. That's it.
Critically damped. Yes. And for R1C1, when not equal to R2C2, that means when the system is overdamped.
So it will be behaving like
This is,
our first problem.
yes. So after, it will like goes like that.
Yes.
This is for overdamped, and this is for the upper is for critically
So
damped.
you can write the zeta values here. Okay. Zeta equals 0, zeta getter 1. Zeta equals 1, zeta getter equals 1. Getter 1.
Yes, yes. Zeta not equal to 0, zeta equal to 1.
Yes, yes. Okay. So this problem is almost
Okay.
done. Okay.
Yes.
And it is a
And
frequently asked
now,
question. Okay, for the second order circuit.
yes, this is in many companies interview. This is a very frequently asked question. Okay, now
We can go to
I
the third
come
question.
about the third question. This question. Okay, let me just copy it. Okay, okay. So again, uh, we can clearly, again, this is an second order RC circuit, and and if we are saying that how it's second order, so same thing applied here. You can set independently the voltage across the two capacitor, or you can check that the current through the capacitor is not equal, right?
Yes, yes, exactly.
Yes. Okay. Now and now we uh, now suppose we are applying a step voltage at V in. Let's suppose a voltage V, step voltage V. So at t equal to 0, what we know, at t equal to 0, we know that the capacitor acts as a short circuit. So this will look like that. Here is R. And so V0 will be whatever the voltage V in. That means 5 volt, or sorry, okay, 5 volt. I just take this as a 5. And after that, t equal to infinity, what happened? The capacitor, all the capacitor acts as open circuit. So here is R, here is V0.
Anindam, make a ground on the above circuit, above figure.
Yes, yes. Sorry, sorry, sorry. So and the t equal to infinity, V0 equal to 5 volt. And if you are drawing, and if you are draw the output voltage like this, that is completely wrong. So at t equal to 0, it's also 5 volt. At t equal to infinity, it also 5 volt. But it is a second order circuit. There is something happened at that position. It's true that its steady state will be reached 5 volt, and at 0 it's also 5 volt. But in the meantime, there is something happened in here. So now we comment about this phenomenon, what happened in the meantime intuitively. So let's redraw the circuit again. This is R. So whenever at t equal to 0, whenever the V in is rising, the capacitor acts as short circuit, and this short circuit and V0 and the V0. Okay, I draw the, and V0 will be reach 5 volt. It is true. So for whenever the V0 is reach 5 volt, so a current will flow through this resistor R, 5 by R. So this current will charge the capacitor C1. So the capacitor C1 is charging slowly. Capacitor C1 is charging slowly, and this current is coming, and this current is coming from the branch here. This C2 and R. So yes, from the branch C2. So this capacitor, the C2 capacitor also charge. So in I can say that. So if the current is coming to the C2 branch, the capacitor, across this capacitor voltage is developed. So I can say that V0 equal to from the and we know that the KVL equation has to be satisfied at every time. So V0 equal to, I can say that V1, sorry, uh, V in equal to V1 plus V0. So V0 equal to V in minus V1. So now you can see this voltage, the V in voltage is constant, and V1 is rising. So
Okay, Anindo, make a V1
the
and
V0 will be,
make a V1 draw like what is the V1
okay, okay,
V1 voltage? Just mention it. Okay, yes.
okay.
Okay.
So V in is constant, and V1 is slowly rising, or V1 is slowly rising. So we can see that a certain drop happened across the certain drop happened at the V0. Yes, and the V0 voltage will falling, and and it's falling up to a certain point, then it rising again to go to the steady state. And after falling and go to the steady state, and basically this is, and C1 C2 values are different, so we can see there the pole are completely at different location, and we can comment about this, that the circuit is overdamped, and this is a passive RC circuit, and the V0 by V in, that means gain of the circuit cannot go above the our input voltage. So
Actually,
the
if
V0
you are
must
seeing it is
drop.
going down at this time, why not is going upward at this time duration?
Yes,
Because this
yes,
is a passive circuit, so the output cannot be more than the input voltage. Okay, so it will be dipping. Okay, dipping in this time
yes,
duration,
yes, yes.
and then it will be rising. Okay, so we will deal with in more deeply intuitively in another video. roughly thinking that the the output at this time duration will be dipping, right? So this is the takeaway.
Yes, yes, yes. And after a certain period, it will again come to the steady state value. That is whatever the input voltage.
Yes, yes, yes.
And actually, the exact phenomenon what happened in this portion take a long duration to explain. The time will be taking the time will be taking so much. So that's why I don't discuss the exact what the phenomena, whatever
Yes,
the current
we will
through
discuss
the
about the
resistor.
process. Yes.
Yes, yes, yes. So the V out, the V in here and the V out waveform is look like that. And I can also uh, okay, I can draw the voltages across the capacitor C2. The voltage across the capacitor C2 will reach like that, and the voltage across the capacitor C1 will go like this and going to zip like this
Yes, yes.
at
Anand,
that
mark,
point.
mark VC1 or VC2 on the graph.
Yes, 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 yes. Just I marking. This is for VC2 and this is for VC1.
Okay.
And the next problem will be discussed by Amit.
Mhm. So the main thing is the output thing. There will be a dip. Okay. In the time
Yes,
between
there will
steady
be a
state
dip.
and zero.
Yes, yes, yes.
Okay. So now, okay, I will be sharing.
Okay, just
So visible, right?
yes, yes.
So now come here. So I have some fun now. So now we have a circuit like that. Okay. So is this a like first of all we need this is first order or second order? You may think it will be a second order because we can set these two voltage independently, right? But actually this is not. Why not? Because we can see that same current is flowing through this both of these two capacitor. Okay. So actually this is a first order circuit. Okay. Right, Anindo?
Yes, yes, yes.
This is actually a first order circuit. Okay. So basically this circuit can be redrawn as the following.
Yes.
Right?
The entire yes, yes. Cause there is no branch. The entire current flow through the only one branch.
So I am not taking the output from anywhere. I am just modeling it like that. Okay. So this is basically a
Yes.
first order circuit. Okay. So now there is another circuit I am drawing. So we need the order of the circuit first. Okay.
From that thing, we can conclude that every time if we see that 2R and 2C, that means it
That
doesn't
doesn't
mean
ensure there is a that
there
is
is a second order circuit.
yes.
Yes, yes.
Now what about that? So it is so we can only like we can set one capacitance voltage across it and then we can like determine the another capacitance like another voltage across its capacitance, right? So this is
Yes.
like definitely a first order circuit. Okay. And you can also think that to need to find the order of the circuit the output will be deactivated, so it will be zero. So we can see that C equivalent and R equivalent is nothing but a only single capacitance and single resistance, right?
Yes, yes.
So this is the first order circuit. Okay. So this is also a first order circuit, not a second order. Okay. So now comes the fourth problem we need to discuss right now. Okay. So let me copy the circuit. So basically this is the what I can say this is the uh, most important circuit. Okay. Like the output will be some different thing, right?
Hmm, hmm, hmm.
which order circuit is this? So this is second order circuit, right? Because we need to set both
Yes.
the state variables
Voltages.
independently, right?
Yes.
So this is a second order circuit, and we can also see that the current through this capacitor is not equal to current through that capacitor. So current of this both capacitor are different. Okay, so this is second order circuit. Now again we are feeding a step. Let's say 5 volt with respect to time, and this is 0, t equals 0. Okay, and this is our V. Now similar thing. So we will try to do at t equals 0. So t equals 0, cap is shorted. Cap is shorted. So cap is shorted means this will be shorted and this will be shorted. So what will be the output? Output will be 0 volt, right? So V out will be 0
Right.
because this 0 is there. Now
Yes.
at t equals infinity, the capacitor are open. So this will be open and this will be open. Again, this voltage is there. So V out is 0, right? So you will find, will it be 0 every time like that? Not, right? Because this is a second order circuit. We cannot do that.
Hmm.
So now, so actually we are feeding a step, okay, but in this particular problem we will be finding a zero at zero frequency. Okay, how to find 0? So we can see that at 0 frequency means at DC, right? At DC the output becomes 0. We can see that. So at DC, so so if you calculate now, so if you calculate V out over V in and in frequency domain, you will be finding this type of things. Okay, let me draw the picture, draw the equation. So it will be SRC by, it will be S square RC square plus 3RCS plus 1. Okay, so you will find this type of transfer function for this particular circuit. So I am not going to do over here, okay, right now. So we can see that you will find a 0 at 0 frequency, right, in this circuit.
Yes.
We
Yes.
have told previously, if we have a step input of a second order circuit, but in this second order circuit we have a 0 at 0 frequency, then it will behave like a impulse excitation, right, Anindo? Like it will feel
Yes.
like
Yes.
a impulse excitation. So what will be our settling behavior of the second order circuit? So we will see. So this will be like that, right, at 0. Okay, so this will be like that.
Yes.
Okay, so
A sudden jump and die out.
yes, this sudden jump is happening for which quantity? This 0 quantity, right?
Zero for the zero.
For the
Yes.
0 quantity, it will suddenly jump to a voltage. Okay, and then we will decay.
Yes.
So what we have told at the beginning of the session, it is like that. Okay, so it will be happening like that. So this case, okay, so this will be there, this thing. Okay, so at t equals 0, we have a like we have sudden jump at the output, okay, due to the 0 at 0 frequency of this particular transfer function. So the behavior will be looking like that. Okay, so this is how you can approach to the interviewer. I think it is very much enough, right? On very much enough to conclude your conclusion,
Yes. As a
conclude your answers
uh,
or at the approach.
yes. Yes. Yes, as a freshers, if you can doing this thing as in interview, then I think it is enough,
It is
more
enough
than
for a
enough.
person. Okay, so we can stop today. Okay, so you can find the transfer
Yes.
function. Okay, so you can see that there will be two poles and the both poles are not equal. Okay, P1 not equal to P2. Okay, but we cannot do the over damped thing case because we have a 0 in this figure. So if there is a 0, we cannot do this type of thing, right?
Right.
0 at 0 frequency. Okay, so this is, and in the all the previous cases we don't have 0, right? Like we have 0
Yes. In
at infinity frequency.
At infinite, yes, yes.
So that doesn't exist, so we haven't discussed it. Okay, so like in previous cases we don't have zero. Okay, but in this particular problem
Yes,
we have a zero. So this is the thing. Okay, so we can stop here, right, Manindo?
yes. I think it is enough for second order. I think it is enough.
For second order it is enough, and we are going to have some discussion on like purely intuitive analysis. Okay, no pole,
Yes, yes.
no zero,
Actually,
fully on
yes,
time domain. Okay,
actually, yes. Actually, at that transient state, actually, how the voltage are changes and
yes,
current are changes.
we will discuss. Okay,
Yes,
basically for this particular two circuit. Okay, like the
yes, yes, yes.
third and fourth circuit. Okay, okay.